Yeah, I'm just going to finish my coffee and yeah, I think we're going to start.
Pero recordarán que ayer me tocó hacer un link virtual para que me corrigieran la clase. De pronto, porque como eso que instalado en esa caja.
So it is broadcast. Okay, perfect.
Pero es fácil, es el N menos y la letra de donde tenés.
¿Cómo es que es el N menos?
Y la
Y la ruta.
Y la ruta donde tenés el punto casa.
Sí.
So I would like to get started. Thanks everyone for coming. I assume more people will just come in the next half hour. Hope you all had a fun evening. I certainly did. And today we're going to continue our lectures with today, this morning talking about disk evolution and dust evolution. But before I start with that, I wrote something on the board. So the data set that we're going to need for the ALMA project is about 20 gigabytes. So that's not going to work downloading as we've seen yesterday. So I put it on this external hard drive that is now passing, it's passing around the room. So on the hard drive, go to the folder ALMA data. Then inside of that you see the zip file from the tutorial from yesterday, which you probably already have. And this folder 2016 blah blah blah. So that's the folder you want to copy to your hard drive. And then after you've copied it, make sure to unzip the zip files that are inside of there. Otherwise you have to do that. Yeah, please don't copy any of the other files. This is all my stuff. Okay, maybe we can close the door a little bit again. It's being loud. Okay, cool. So then for today we're going, or this morning we're going to talk about disk evolution. So this is the table of contents of today's lecture. Also, the lectures are available on the website of the school. And if you, so you should, do you all have the address of that? Okay, good. So you can download this lecture also this afternoon's and tomorrow morning. They're all available on the website. And yeah, so for today, I'm going to start with just repeating the general picture of our understanding of gas and dust in the photoplanetary disk. And the first half of the lecture will be about the gas disk evolution, and the second part about dust disk evolution. And these are two separate things. And this is something that is slowly becoming more clear also from our observations. That because in the past people used the dust often as a tracer of evolution, this has led to some confusion in how the disk evolves and how you can trace that. So I'm actually going to end with a few examples of different evolutionary features based on the combination of gas and dust evolution. Okay, so let's start again with our general picture of a protoplanetary disk. Looking at the disk from the side, we know that there's gas present, the disk is flared, and then there's also dust particles. Dust particles can coagulate and in that way grow to larger and larger sizes. They will, what we usually see is that the largest grains are located in the midplane, the smaller grains are located higher up. We're going to see today why that is. And you can observe the disk in many different wavelengths. You're going to remember that in the submillimeter we're sensitive to the larger grains located in the midplane. The emission is essentially optically thin. While the scattered light is tracing just the surface of the disk, and the infrared is only also kind of tracing the surface, but only in the inner part of the disk. But this is just as a bit of a reminder of what we talked about yesterday. Also remember that we often use this assumption of the ISM ratio between the gas and the dust when we're calculating masses. So if we have a dust mass multiplied by 100, that's often taken as the gas mass. So if we then take a look at some observations, this is an example of either the Hayat, one of the most famous photoplanetary disks, essentially because it's relatively close to us. So this is, we see here the integrated 12CO emission, so tracing the gas. We see that it's rather extended compared to the millimeter dust continuum that's shown over here. So you can see the gas is larger than the dust, but the dust is actually showing tiny dust rings as well, so a little bit hard to see very light. See, you can switch on the light. Okay. Is this okay?
Yeah,
okay. Good. And then in here, for that, we're essentially looking at the scattered light of the surface. We're looking at the height. We look at the surface of the disk. We're tracing the small grains. So essentially now we have gas, we have small grains, and then millimeter dust. And you can see that they're all tracing different components. That all these different components also have very different distributions. They're located in different parts of the disk. Okay, so let's go for a little bit of history of how do we know that gas is present in photoplanetary disks? Because we talked yesterday a bit about the history, about the infrared excess and SEDs, so this was all dust emission. But there's actually also a paper from the 80s, and it was, I think this is the oldest paper, where they were able to measure CO 1-to-0 emission with an old interferometer. I forgot which one, it doesn't exist anymore. And it's a little hard to see, but this is a channel map. So here we have the velocity 7 kilometers per second, 6.6, 6.1, and 6.0. And if we now look at the solid contours, you see here there's and the star is right here, right? So here we see that the channel, the emission of the channel is located to the right. And here it kind of goes at the same position as the star. Then one step further we go to the left of the star, and here we are all the way on the left of the star. So you need to have a little bit of imagination. This is very low signal to noise data, but this was essentially the first evidence that there is rotating gas in around a young star. And remember, this was 1987, so it was very, back then this was a very big deal, I think. I was very little. So what we actually see here is the analysis that they did. So obviously, like looking at the channel, it doesn't look very convincing, but you can actually take this position velocity diagram where you measure the location of the emission and the velocity for each, essentially for each channel, and there you see that the velocity really follows the Keplerian motion that you expect around a certain stellar mass, in this case of HL tau. By the way, yeah, I should have mentioned that too. This is HL tau. This is like that very famous disk that has these beautiful dust rings. They didn't know that at that time. This was just chosen because it was like this. Okay. Now, the second reason that we know that gas is present is that we were able to measure accretion. And I briefly touched on that yesterday. The two ways to measure accretion is both by UV excess in the SEDs. So remember, this is the flux as function of wavelength. We see here the photosphere of the star, the body of the star. We see all data points showing that there's infrared excess from the dust. And then here at the shortest wavelength, you see again that the measured flux points are not exactly following the photosphere. They are above the photosphere. So this comes from UV emission that is generated by the accretion shock onto the stellar surface. And we actually see the same thing for this is much newer than it. This is a high resolution spectrum. So now we're looking at a spectrum between 2000 and 6000 angstrom, so 200 to 600 nanometers. So it's kind of like this zooming onto this very small part of the spectrum. In a regular stellar photosphere, the black body would kind of drop off like this. But what was measured is actually this huge offset, and on top of that, you see all these different lines. But in such a spectrum, you can really see the combination of the UV excess and all the lines that are indicating accretion. And the UV accretion luminosity can be converted relatively simple. There are some equations for that to an accretion rate, which we express in solar masses per year. So that's the amount of mass that accretes onto the star every year. So how does accretion work? Well, this is it's actually not that simple. It has to do with magnetic fields. And you may know this joke about astronomers and magnetic fields that we think they are there, but they're impossible to measure. And if you present a model, then somebody may raise this. So what about magnetic fields? Have you considered magnetic fields? Yes, simulation. And usually the answer is yeah, no, because we have no idea what to do. But for understanding of accretion, we do kind of need these magnetic fields, and it's, at least from the physics perspective, this is pretty well understood. So we have this the hot inner material of the disk is funneled through the field lines of the magnetic field from the star onto the stellar surface, where you then get this accretion shock that results in this very hot continuum emission, like 8,000 to 10,000 Kelvin, and that leads to that UV excess. Remember, this UV excess is essentially another black body at a very high temperature. On top of that, you get these emission lines. Okay. So here are just a couple of other examples of how to measure the accretion. So what you often see in papers is this measurement of the so-called H-alpha line. So the H-alpha line is located in the optical part of the spectrum, and when you essentially measure the broadening of that line, so you can see here the width in velocity space, that essentially tells you about the accretion rate. You can convert that more or less to the accretion rate. The problem though, and I put this as a careful note, there are other physical mechanisms that affect the width and even the detection of this H-alpha line in stellar surfaces. So it's not only tracing accretion, it can trace other things as well. In several papers in the 90s and the 2000s, people were using only H-alpha to measure an accretion rate, and it's been shown that those measurements are sometimes completely wrong because other processes played a role as well in this distinction. So the proper way to measure accretion is to really do this combination of measuring UV excess and the width of H-alpha and several other optical lines. And an example of that is shown over here. So again, we see flux as function of wavelength. These kind of spectra can be taken in one go with the X-shooter instrument, where we measure from essentially 0.3 or I think even 0.2 micrometer, like 200 nanometer, all the way up to 3.6 micron with, here in near infrared we're missing parts because of the absorption. You essentially have a full overview of the stellar spectrum, and with that, by fitting a photospheric model that includes accretion and various rates of accretion, you can derive both the spectral type and the accretion rate. So this is the papers that use this method can be, those accretion rates can be trusted really well. Other papers that only use the H-alpha line rate just have to be a little bit careful. Okay. So, if material falls into the star, and this is, we have this, essentially we have to consider that material moving inwards, while at the same time the system as a whole must preserve its angular momentum. And this idea, this is the way to do that is by considering the system as an accretion disk, and that's actually the same as a black hole accretion disk. Even though the conditions in the black hole accretion disk are very different from a protoplanetary disk, the idea of how accretion and angular momentum is managed is considered more or less the same. So this is right, in some papers you will actually see that they simply describe it generally as an accretion disk. So we see another. We see an example of this angular momentum preservation if we look at the solar system, because we know that the sun contains almost all the mass in the solar system. So the sun is much more massive than the planets, right? But it's rotating very slowly. It only contains 2% of the angular momentum. On the other hand, the planets altogether contain 0.1% of the mass and 98% of the angular momentum. So this is essentially showing that you can have a mechanism where mass is transported inwards, angular momentum is transported outwards. And the way to imagine that in a disk is kind of by this toy model. So say you have a disk, you have a ring of material A, a ring of material B, and we know from the laws of Kepler that ring A is moving faster than ring B. Therefore, you will have a bit of friction between A and B, and that means that A is being slowed down and B is being sped up, and that is essentially that's transport of angular momentum from inside to the outside. Angular momentum can be expressed just based on the stellar mass and location, and as a consequence of this process, as soon as your ring A loses angular momentum, mass must be transported inwards, and this is essentially how we can understand that material falls into the star while the disk remains. And the result of that is that ring B moving outward means that the disk itself starts spreading out according to this disk model. So this model is also called the viscous disk model. Viscosity is, of course, has to do with the fact that A and B move alongside each other and experience this friction. We can also call that viscosity. Essentially, oh gosh, I don't know the English word for that. The viscosity tells you like how easy a liquid moves. Like for example, syrup has a much higher viscosity than butter. You understand this? How it flows through, like even through a glass. If you pour syrup in a glass, it's very thick, and water is very thin, so it has a different viscosity. Okay. So this viscous disk model can be described by this thing called the diffusion equation, and it's again one of those scary equations that don't worry too much about it unless you're going to do modeling, which we won't do this week. We're just doing observations. You don't need to understand all the details here. But what it describes is the change of the surface density. So this is a differential equation. Change of this surface density as a function of time, and then this. So you essentially have this component minus this component minus these two components has to equal 0. So essentially you're trying to find a solution for the surface density as a function of time and as a function of radius that satisfies this equation. And so the other terms that we have are this is the viscosity of the disk material. It's the factor nu here. And here we have the angular momentum term and infalling material term. These terms over here can be neglected when we get to the protoplanetary disk phase. They are more relevant in the early stages when material is also still falling onto the disk. But as soon as we're in the protoplanetary disk phase, they are so small that they can basically be ignored. So it makes the equation a lot simpler. And so now we have this like, simple differential equation with only a couple of terms. And one of the ways to solve it is by this prescription. This is called the self-similar solution by Lindenthal and Pringle. You will see this citation basically in any paper that is describing gas disk evolution. So now we have an expression of the surface density as a function of radius and time with a number of expressions. So we have the large T, and this is a little bit confusing. This large T is not the temperature; it is actually a function of the that contains the time. So how things vary with time, normalized by this viscous time scale, T. And then we have this RC, which is more like an effective radius, and this gamma factor, which is often set to 1 in order to simplify the equation. Again, so this is just a description of how the surface density evolves with time. Okay, there was a double slide here. So how does that look like? Here we see this self-similar solution plotted, which I always find a lot more intuitive than looking at an equation. So now we have the surface density as a function of radius, and if we look at the curve, we see that they're tracing time steps of 200,000 years. So here, the purple curve is the beginning, is how the surface density looks like at 200,000 years of age, and then here's 400,000, 600,000, 800,000, and then the green curve becomes the 1 mega-year curve. So what you see is that the surface density profile flattens over time. Essentially, it spreads out, but also decreases in the center. And this means that we have this. Now we have a description of how this evolves, but we need something that provides this viscosity, that provides this viscous stress. And this is still one of the big mysteries in protoplanetary disk studies. What is the origin of this viscosity? How do we get this viscosity, or actually this turbulence in the disk that can help to make this whole thing work? Essentially, to have material falling inwards and spread the disk outwards. Because at some point, not molecular viscosity could play a role, but that one is much too small. But there's this other idea that is called turbulent viscosity. So now we have the effective viscosity that we use in our surface density equation, and that effective viscosity depends on the degree factor, the sound speed, Cs, and the pressure scale height. So essentially the thickness of the disk. And then finally we have this factor alpha. The alpha is a term you will often see in protoplanetary disk studies. This is just a fudge factor. It's a constant. It's usually taken like by orders of magnitude, so it's like 10 to the minus 2, 10 to the minus 4, 10 to the minus 6, etc. So by setting that alpha to a certain number, you now have something to describe the viscosity in the disk, without actually having to worry about what provides. In theoretical work, they still try to calculate this alpha value. But the nice thing about this equation is that you don't actually need a hydrodynamic model behind it. You just use it as a way to describe how it is. And so it means that in many calculations we just assume some kind of value. You always see this listed in the paper. We assume this and this alpha, and based on that we let our disk evolve and we let all the things in the disk happen. It's also called the alpha disk theory. So the way to think about this alpha term, about this turbulence in the disk, as I mentioned, there are a lot of material hydrodynamic simulations where they try to essentially trigger some mechanisms or some instabilities in the disk that will provide that turbulence, that will make sure that things are moving around. These are often done in what we call a small box, so they don't actually calculate this process for the whole disk. They just take one box, like one location in the disk, and that's where they calculate things as a three-dimensional box. So they don't actually consider the fact that there's a star and that things are rotating, etc. Just only calculate conditions there. Then there are a number of instabilities that have been proposed in the literature. I don't want to go through all of them because honestly I find them very confusing, and it's none of them have been proven to be the main contributor. So there's baroclinic instability, vortex shear instability, and finally the most popular one, magnetorotational instability. So this instability arises because of magnetic fields, which we can't really measure. It assumes that the gas in the disk is ionized. And ionization of molecules can happen either because the molecules are colliding with each other, so if you have fairly high densities, or because of the radiation from the star. Both of those processes will ionize the molecules, and depending on where you are in the disk, one of the two the assumption is that one of the two will be enough to ionize a sufficient amount of the gas material. If gas material is ionized, that means that you can tie it to the magnetic fields, simply how the electromagnetic equations work. As soon as you have material tied to the magnetic field in sort of ideal NHC conditions, it means that if the material itself moves, for example through circular motion, remember it's orbiting around the star, because of this magnetic field in combination with that displacement, you get an instability in the fluid that will enhance that displacement. So essentially things are orbiting, but because of that magnetic field factor, it will also start moving in the orthogonal directions. And so this is essentially providing turbulence. It's due to the interaction between the magnetic field and the ionized material. Well, there are some issues with that, and I'll come back to that later. But this, I hope this gives you a bit of an idea. MRI is a hypothesis for providing turbulence that we need in order to explain how the disk evolves. So none of this is really proven and really fully modeled because it's too complex. And it's also really hard to constrain because we can't measure magnetic fields. Okay, so with that viscous disk model, there's a famous paper, Hartmann et al. 1998. He used this viscous disk model in order to explain a number of his observations. So what he measured was the accretion rate for a number of disks. These are all the data points here, the accretion rate, and all these disks have their own age. And so unfortunately I didn't have this plot without the lines. he managed to say, he managed to draw a line through all these data points, but if you kind of squint, it actually looked like a scatter plot. I just want to start a problem with that. But he says, well, even though there's a lot of scatter in this plot, the accretion rates and behavior of these accretion rates is consistent with this viscous disk model, where the surface density drops and therefore also the accretion rate drops over time. Then the predictions from that same viscous disk model, and it shows like a couple of variations, that's why there are multiple lines. So this main solid curve, that is the solution model. That same model predicts, of course, that the disk size increases over time. But there were no data points. There were no measurements of the gas disk size. So this is just the theoretical prediction. And then finally, there's this third component, that is the disk mass itself, that drops over time. So here, he actually used this assumption of like, oh, we take the disk mass, we multiply by 100, and that gives us the disk mass. Also here, you need a little bit of imagination to say, yeah, these data points really follow this curve. I'm not saying they are opposing it, but it's like looking back at this plot, it's not actually that convincing. But in the paper, he describes it as like the ultimate proof of this disk model. I'm going to have better arguments than this with newer data. But I was recently reading this paper again. Like, oh my god, it really is not that convincing. I don't know why he managed to publish this. But I guess it was because it didn't like totally rule it out either. Sort of order of magnitude, it's okay. Just that the trends are not really there. And so based on all these models, he assumed an alpha 10 to minus 2. He also tried different alpha values and then found essentially worse fits. And a disk lifetime of 2 to 3 million years. Okay, so I mentioned this in the opening lecture. There's another process that clears the material from the disk. That's called photoevaporation. The idea of photoevaporation is that the radiation from the star heats up the surface layers of the disk that will essentially exceed the escape velocity and then get lifted off from the surface. So this is the photoevaporated flow. So in the very inner part of the disk, it's not going to work because there all the material is hot and ionized, it will not escape. But just outside of that, the photoevaporation becomes active and then lifts off the material. I also mentioned that as soon as you remove material from the surface in this way, it immediately gets replenished because material from the outer disk is transported inwards, right? So for the accretion. However, when the accretion rate has dropped significantly, it cannot replenish this photoevaporative removal quickly enough, and then you clear the entire disk. So that looks like this. So in stage 1, you have this photoevaporative flow. You may have an MHD disk plate. You have material accreting onto the star, but everything things move inwards and upwards, but everything keeps getting replenished. However, when the accretion rate and the surface density drop below a certain threshold, you remember that the inner part of the disk, because it's too ionized, is not going to be cleared by photoevaporation, so it's a little bit further away from the star. You start to form a gap. And as soon as you form that gap by the photoevaporative clearing, the inner part is cut off from the outer part, so you lose that inner part really quickly. And eventually also the outer part of the disk will get irradiated and be blown away. So to look at this, we've also seen this plot before. Also here we see the surface density as a function of radius. Initially it's pretty high, but over time when it drops and suddenly that gap is opened, as soon as that gap is opened, it widens up and eventually clears the entire disk. So this is the final removal of the gas. Initially, you're just slowly dissipating, you're slowly decreasing the total gas mass, but as soon as photoevaporation kicks in, it happens really quickly. And yeah, as here we see, we see the same story again. So here we see a little bit more of these steps in between. Initially a rather compact, a somewhat more compact disk that spreads out. This is this, it starts to lose gas density overall until a gap opens and the gas dissipates. So, I've so far been talking about internal photoevaporation. Photoevaporation as the result of the radiation from the star. There's also something called external photoevaporation, and shouldn't confuse it. So external photoevaporation, the physics is the same. It's radiation heating up the gas, detaching it from the surface. But in this case, it's not caused by the star from the system itself, but by the external radiation field. And this, so that means from other stars in the area. Usually, other low mass stars are not really bright enough to have any effect. But there are these very massive stars called OMB stars that are present in some of the star-forming regions. And they provide a radiation field that is so incredibly strong that it really starts to affect these, it really starts to dissipate gas disk from the outside in. So the other one was essentially from the inside out, but this one works from the outside in. And that leads to faster mass loss, so kind of on top of the physics disk model, and therefore shorter disk lifetimes. And we see that here in this plot. So so this is the disk mass loss rate. So essentially how much mass is lost over time. This function of time. And they show it for different strengths of the UV field. It's expressed in G naught. So G naught is again, sort of the ISM UV field, normalized UV field. But if it's 50 times, 500 times, 5,000 times stronger, like you see is that the mass loss rate becomes, sorry, let me say this properly, that the mass loss rate diminishes the lifetime of these disks much more quickly. And we actually see evidence of this in all observations of the Sigma Orionis region. The Sigma Orionis region is a small star-forming cluster with a very big O star in the center, Sigma Orionis. And so this is a map of the region where the stars that have a detection in gas, or 12CO with ALMA, are encircled in blue. And the ones with detection in dust are encircled in orange. What you notice is that there are no disks with gas close to the star. They all happen to be further away. But also, if we look at the dust mass as a function of separation from the center, we see that the dust masses only become large when we are basically more than 1 parsec away from the center. So this observational evidence that disks are dissipating faster or maybe are born smaller when they're too close to an O star, when there's a strong external evaporation, photoevaporation field. Okay, so now we want to make some estimate of how long this process actually takes. If we have this viscous disk model, we have some factors that determine like how long does it take before the star, before the disk is at the end of its lifetime. And this was estimated in a very simple way. We look at a number of clusters with different ages, and in each cluster we count the number of accreting stars. This was done in 2010. And so here are all the data points, and they're data red, or this is just like data from this guy himself and data that he took from literature. And as you can see, the number of accreting stars quickly drops as a function of age. And he estimated that this drop has a half-time of about 3 million years. So, also briefly mentioned this yesterday, the typical gas disk lifetime should be about 3 million years. An alternative, and this is actually a plot that I showed yesterday, is to do the same exercise, but now looking at the fraction of young stars that have a disk, that have infrared access. So also here, we look at a number of clusters, and then we separate our stars in an SCD with a strong infrared access or a class 2 source, such as this example over here. And then we also have stars that have a weak or even no infrared access, just background, but that star is part of the cluster. And yeah, so this adding up all of them, and then dividing the number of disks by that total number gives you that disk fraction. And sort of almost, yeah, almost not surprising, this plot and that accreting star plot looked really similar. So essentially these blue data points are taken from this plot. So what they found is that the number of accreting stars drop equally fast as the number of young stars with infrared access. And so therefore this lifetime of 2 to 3 million years also matches well with this prediction of the viscous disk model in that paper of Hartmann. And this number is still used in most papers today as the real disk lifetime, also in planetary ecology. And it's almost funny like how simple these plots are to obtain such a fundamental parameter, which is the disk lifetime. And the reason why I'm a little bit skeptical of this is not just because of the Hartmann scatter plots, but also because of the issues with this disk fraction plot. Because first of all, how do you measure the age of a group of stars? It's a question to you. If I have a group of stars, how do I know the age? Sorry?
With the help of
Yeah? So, I'm sorry, I've done a quote about
Maybe with the models of isochrones that we have obtained.
Very good. With isochrones, with a visual muscle diagram. Then, second, how do you measure the cluster membership of a group of stars? So, if you have a group of stars that are located more or less in the same position of the sky, we tend to assume that they all belong to the same cluster. But how do we know for sure? Yeah.
We paralyze the subproper motions.
Really good. You've seen my next slide. Yeah, so the ages are estimated by a Russell diagram. Cluster membership is determined by parallax, which gives you the distance, but also the proper motion, because cluster members tend to move at more or less the same proper motion speed, so usually measured in milliards per year. The issue is that the ages of young clusters are pretty uncertain. This is an example of isochrones in the lupus star forming region, and we can see. I think the ages actually dropped out of the plot, so that's really ruining my point. But so the red lines are the different ages in the plot, and the blue lines are the different stellar masses. As you can see, these data points, or the luminosity and the colors, they cover a pretty wide range of ages. So you essentially, if you say this is the age of the cluster, you're just talking about the average, because there's intrinsically a large scatter. So there's that issue that the ages are always uncertain. The second part, and that is actually even more important, is that the Gaia is that before the Gaia mission, there were no parallaxes and proper motions known of these nearby young stars. So the distance to these young clusters was estimated based on the parallax of the one bright star. All the other stars were assumed to be part of the same cluster just because they were located in the same part of the sky. With Gaia, the Gaia Beta Release 2 in 2018 finally gave us parallax to the proper motion to all of these clusters. And now there are a bunch of papers where they have new catalogs of these are the real cluster members. So this means that we can actually do better now in terms of energy. However, both of these effects turn out to be not even that important because I think it's clear I redid this calculation together with the student. These two effects were actually not that bad based in that disk lifetime plot. There was a third issue with the disk fraction plot, and that is that they were not considering the environment. They were not considering that several of these clusters in this plot were located in a region that had an OB star. So where we know that the disk lifetimes are significantly shorter. So if you want to measure the disk lifetime in your typical star-forming region without an OB star, you cannot combine those data points, which are these ones, with regions that have an OB star. So me and my student, we essentially redid all the calculations of the disk fraction, the ages, and then also picked out all of these clusters that had an OB star. And with that, we created this new plot of the disk fraction age. Now we have a best fit of the disk lifetime of 8 million years. Actually, a year later, another paper came out where they did something rather similar, but they simply divided up clusters in less than 200 parsec, 200 to 500, at different distances. They found that the further away the clusters are, the shorter the disk lifetime. So that's pretty interesting as well. But we have to remember for the disks that we are mostly studying, the disks that are close to us and at 100, 200 parsec, the disk lifetime is closer to 8 million years. And yeah, this is a pretty recent result. It's not used that much yet in literature, but I hope that will change because obviously it has huge consequences for understanding of, for example, planet formation and disk evolution. Okay, so this was the update on the disk lifetime. Now I want to talk a little bit about that turbulence, about that alpha parameter, this fudge factor, which was claimed to be 10 to the minus 2, because that was consistent with the viscous disk model, was consistent with observations. And the turbulence parameter, because it's important in many of the hydrodynamic processes in the disk, there are many indirect constraints from observations. For example, the turbulence of the disk will set the intrinsic line broadening. So molecular line, of course, is broadened because of the capillary motion of the disk, but also because everywhere in the disk things are moving around a little bit, you get some very small broadening as well. So you need really high spectral resolution to measure this, but this has been done by Flaherty et al. For a couple of disks. And essentially what he measures is that the observed spectrum, that's shown in black, is not consistent with the turbulent velocity of 0.1, but something that is expected from the sound speed, but something that is at least 20 times smaller. And so based on this, he sets the turbulence, the alpha turbulence at 10 to minus 4. Something similar you can derive from these images of HL. Where we look at spontaneous emission. So we have all these dust rings, but the disk is a little bit inclined. So based on that, the fact that we can observe the gaps throughout the disk, that there's no shadowing in the disk, tells us that the disk must be extremely flat. So the millimeter gauge must be extremely silent. Also, this implies that the turbulence is very, very low. Because if the turbulence was higher, your dust would be stirred up, and you would see that as shadowing. Then this is actually coming back to this MRI, which was thought to provide the turbulence in the disk. Well, as it turns out, a large portion of the disk is not very well ionized. That's also called, that region in the disk is called the dead zone. This dead zone means it's a region of low ionization. It's a region where the magnetic fields, if they were there, don't have any effect, don't help to provide turbulence, and therefore angular momentum cannot be transported. And this is actually only found if you include non-ideal MHD effects, so kind of additional MHD effects in your simulation. It turns out that the MRI only works probably in the very inner part of the disk, but not in the global angular momentum transport picture. Then the question is about this viscous spreading, because this was another consequence of the viscous disk model, is that the gas disk increases in size over time. So if you want to measure the gas disk, we usually go for CO, because that's our most common molecule. We'll talk a bit more about CO analysis tomorrow morning. And then we can measure the radius of the CO as a function of age. And in this paper by Tappel et al., they ran a number of viscous disk models. So 10 to minus 2, 10 to minus 3, 10 to minus 4 in different colors, green, blue, and dark blue, for different stellar masses. So these are the modeling results. As you can see, the disk size no, I'm confused. Sorry. This is the disk size with respect to the effective radius. Let's ignore this one. Sorry, I mostly want to talk about this one. Sorry, I'll remove this one because now I'm getting confused with what I want to say. We're just going to look at this plot. It's showing the gas disk size as a function of age for these different alpha values. And in black and purple, we see the data points from lupus, the young starving region, and upper skull, an old starving region. Clearly, the expected disk sizes from a viscous disk model for 10 to minus 2 are not consistent at all with the measurements. Most of the measurements, and it's not like, they don't really lie on this line, but at least they lie well below the 10 to minus 2. So also here, based on the measurements that we have of the gas disk sizes, it doesn't seem likely that viscous spreading is really happening. That viscous spreading must be, like, the amount of spreading is really limited, and therefore alpha may be as low as 10 to minus 4. Finally, there is another piece of evidence that the viscous disk model may not really work, and that is by looking at the accretion rates. Because you remember that I showed you this plot from Hartman, this scatter plot with accretion rates that seemed to drop over time, if you want to believe it. Obviously, these were measurements from the 90s. These were actually these H-alpha measurements that I was talking about before. If you take proper accretion rate measurements from the last couple of years, and you plot those accretion rates as a function of this dust mass, what you see is that there is an enormous scatter, so in the accretion rate as a function of disk mass, but more importantly, the scatter in those accretion rates stays the same. The values of the accretion rates stay more or less the same, whether you look at a young cluster of 2 million years or a cluster of about 10 million years. Also, this is not consistent with the viscous disk model. So now my question is, if the viscous disk model doesn't work, is there another way to get rid of angular momentum? What do you think? You think of that black hole accretion disk model. There was something else in that picture. Jets, very good, very good. So, an alternative way of getting rid of angular momentum is by ways of a jet or an MHD disk weight. You can use those terms almost interchangeably. So the MHD discipline model can again be described by this really fun differential equation, but now with additional terms of this discipline in order to get rid of your angular moment. There's this paper by Tabone where they essentially do all the math. They kind of show that this reproduces the accretion rates and the viscous spreading rate, but they reproduce all of these observables quite a bit better. And in that way, you can indeed have a very low alpha value, something that where essentially turbulence is not that you don't really need that turbulence in the disk. You just need something to get rid of the angular momentum in the form of that discrete. So the main differences are summarized in this very nice figure, where here at the bottom we have the viscous driven disk, where, as I mentioned, you have turbulence, viscous expansion, and material accreting onto the star. And in the top we have this MHD, discrete-driven model or jet-driven model. Material also accretes inwards, but angular momentum gets pushed away by this wind. And the consequences of both models are summarized in these plots over here, where you can directly see what you would expect. So for viscous disk model, so you have to follow the arrows for following the time. Essentially, as a function of time, your disk mass decreases, right? So disk mass goes up this way, the time goes this way. Your disk mass decreases in both cases, but in the viscous disk model, the disk radius goes up. In the MHD, the disk radius goes down because your disk shrinks. Essentially, this is just because there's no spreading and therefore material is transferred. Therefore, the accretion rate, things become a little bit more subtle. So again, time goes from right to left. In both cases, the accretion rate will drop over time. It will drop much more rapidly for the viscous case. This is essentially because the radius goes up while the mass goes down. So your surface density goes down. So in the viscous case, your accretion rate drops very quickly. In the MHD discrete case, the accretion rate also drops, but just much more slowly. So that's why we may not simply measure it in that accretion rate. And then, this final, let's skip over that last block because that's a little hard to explain. So there is one very beautiful example of observational evidence of a disk wind. That is this disk, HD166296. This disk actually has an optical jet. That also is observed in observation. But ALMA, on very large scales, has found this really beautiful rotating disk wind evidence in the 12CO. They were able to measure the mass loss rate, so how much mass is actually being kicked out by this disk wind, which is like 5 to 50 times larger than the accretion rate, and that is 100% certain that must be an MHD disk wind rather than a photoevaporative wind. Because remember, a photoevaporative wind is something that happens only when the accretion rate has dropped below a certain threshold. So the photoevaporative disk wind would always have a mass loss sort of similar or lower than the accretion. Similar or only slightly above the accretion. This is the only observed disk wind with ALMA so far. I mean, it's an observation in 2021, so it's fairly recent. And no other disk winds like this have been found, but we have to remember this is the brightest disk that we know, and you need pretty deep observations in order to spot it. So it's probably just a matter of time before we can detect these disk winds around other sources. Finally, there's this review paper. Actually, I do not point this out. So sometimes I say this PP VII, so that means PP7. This is Protostars and Planet 7, which is a conference that will happen next year, where they have to write review papers beforehand. People who want to give a talk, they have to write a review paper beforehand. This conference is held every 8 years, and That means that the review papers give an overview of everything that has happened over the last 8 years. So all these papers that have this PP7 are a really nice overview of the current status of the field. I've been using the figures a lot for all of my lecture slides, so as a sign. This particular paper is only about disk winds, both photoevaporative and MXD disk winds. They make a very clear case that there are signatures of disk winds in many, many observations from near-infrared, mid-infrared, optical, and millimeter, but that at this point it's really hard to derive whether they're caused by MXD disk winds or photoevaporative winds. So for this is essentially still a topic of study. Okay, so summary of the gas evolution. The gas disk is really difficult to trace, and this evolution process is still poorly understood. So basically, we're screwed. We just don't really know what's going on. We have a lot of ideas, we have a lot of theories, we have a lot of observations. It all kind of seems to work, but not exactly. So there's simply a lot of work still to be done. There's still many of current studies that use the classical physics disk model with a high alpha and with a short disk lifetime that probably need to be updated. So just something to be aware of when you read disk papers, that they may use these old assumptions, even though in the last few years there is so much evidence now that this old model doesn't actually work. And finally, it's important to remember that millimeter dust does not follow the gas as a result of dust evolution. That's what I'm going to explain in the second part of the lecture. But now we're going to take a 10-minute break. Thanks. And yeah, there's still coffee here in the front for people who came in late.
Coffee time.
Coffee time.
Thank you. I think I will stop this.
Oh, okay.